In DSMA 6, we're going to look at solving radical equations. We need radical equations for all kinds of things that we do, but engineers use them, architects. I can't even begin to tell you all of the places that we actually do solving radical equations. All right, so let's do a quick look at vocabulary. So when we have a radical, it's a symbol that looks like this. Usually there is an index sitting right here, unless it's a square root. So if it's a square root, it looks like this without an index. It has an implied 2 sitting here. Okay, and so what that means is we're looking for a number that when it's multiplied by itself, it equals what's underneath the radical. Okay, so this is the radical symbol. We have the index right there. Whoops, my stylus isn't working too well. And then underneath is called a radicand. We don't say that word very often, but I kind of like it, so I say it. That's the number that's underneath. So up here in this case, we have the square root of 9. So what we're looking for is a number that when we multiply it times itself, we would get 9. And so that would give me 3 times 3 would give me 9. And so the square root of 9 is just 3. At that point, we would drop the radical. This is a perfect square. Doesn't always happen. Now, you don't have to know all your perfect squares because the calculator is going to do that for you. I'll probably show you on the next slide how the calculator works. Now, sometimes, though, we have a different number in here. So let's say we have a cube. We call this a cube root. And so it might look like this. And underneath, let's say we have an 8. So this time we're looking for a number that when we write that number 3 times, the same number, we get to that 8 that's underneath. So 2 times 2 times 2 would give me 8, and therefore the cube root of 8 is equal to 2. Again, we can put those in our calculator as well, and I will show you those. But I just kind of wanted to give you a background of what a square root and cube root look like. Now this is a square root of negative 64. I'm going to pull up the calculator in a second and show you that you're actually going to get an error with any roots that are even. So square root, a fourth root, and whatever, a 10th root, we cannot have a negative under the radical, because if I'm trying to find two numbers that when I multiply together I would get negative 64, it wouldn't work. Because if I try negative 4 times negative 4, that's going to get me back to, oh, what am I doing? 8, excuse me. Negative 8 times negative 8, that would get me back to a positive 64. That's not what I want. If I try to do one sign of each, well, that's not a square root. So that's not going to work. And so actually we're going to say that this is not a real number. We will deal with this a little later in the class. It's called imaginary numbers, and we need them. We use them in electrical engineering. You would not have a cell phone if we didn't have imaginary numbers. All right, so I'm going to pull the calculator up and show you what's going on. Okay, so in your calculator here, I know your calculator is a little bit different than this one, but we've got some of the same keys on the keyboard. We're going to go in and grab the square root key. If it's not sitting there as a key by itself, it might be above the x squared key. If that's where it is, what you're going to do is hit shift and x squared, and that's going to give you a square root. Now for a negative, you want to use the key that's right here. Again, might be in a different place in your calculator, but that is the negative key that we're going to put underneath. So as soon as we get the square root box, we're going to put negative 64, and then we're going to hit equal, and you're actually going to get an error at that point. And that's because this expression is not a real number. okay, we would have to move on to imaginary numbers. So if you have a negative number under a radical, that's a problem. You're going to get an error in your calculator. And we're going to, for now, just say that that is not a real number and not actually give an answer. Now, you, of course, can let your calculator do the work here, but a square root or any root, a cube root, a fourth root, they're going to act like grouping symbols. So remember when we did order of operations, please excuse my dear Aunt Sally, you have to take care of what's inside the radical first. So in this case, 25 minus 16 is going to give me 9, and then the square root of 9 is just 3. So that's nice. Okay, so I found the right emulator for you guys. Whether you have a 9860 or this is a CG10, the keyboard's about the same. So this is what I was telling you on that last slide. If you hit Shift X squared, you're going to get the square root that's on top. See how there's a little yellow or orange above the X squared? That's a square root. Now, if you click this one next to it, we call that a caret key. The caret key gives you an exponent. So you're able to enter anything into the exponent and not just x squared. But right above it is a radical with a little x in it. So if you hit, oh, that doesn't look very good. So that's supposed to be a caret key, right? It's supposed to look like this. So if you hit shift and the caret key, then you will get a radical, but you'll get a box here for the index and a box for the radicand, and you can put in what you need. So at that point, you put in the 3 right here, and then use your arrow keys over here, that circle are your arrow keys, and move to the right, and you can put 729 in here and click equal, and you get the answer. This would be 729 is 9 times 9 times 9. Okay, so 9 is the cube root of 729. Again, not that you have to know all of your roots because you have the calculator to help you out. Now with a cube root, because the index is 3, we actually could have a negative underneath because it would be a negative times a negative times a negative. So 2 negatives would undo each other, and then you would have a negative left. Okay. All right, here's what I was talking about, is we can have a negative under the radical if the index is odd. So 3, 5, 7, 13. But still, be careful with your calculator. You want to use that caret key that has the radical where you can, that's right here, where you can put in the index. Now your negative key is down here. It's very important because not so much for this screen, but for the when we start graphing, the graphing part of the calculator is really picky about whether you use a negative or a subtraction, and they will give you an error message and you're not going to get your graph. So the negative is right here, the subtraction is over here. And it's very hard to see in the calculator, but the negative really is a little bit smaller than the subtraction. So at that point, you can put your 3 in here, right arrow over, put negative 64, and lo and behold, you get the answer of negative 4. Okay, so 64 is one of those rare numbers that is a perfect square and a perfect cube. It's actually 8 times 8, so it's a perfect square. It is also 4 times 4 times 4. It's a perfect cube. And in this case, it would be negative 4 times negative 4 times negative 4. Well, negative 4 times negative 4 would give me a positive number, and then times a negative number again, I would end up with negative 64. So one of those fun facts to know and tell. All right, so we're going to put negative 4 in here. Again, don't forget to drop the radical. If it's a perfect radical and you get a perfect answer like this, where the radical is gone, you want to keep the radical gone. All right, let's take a look at how we would get rid of a radical. These are inverses, and you're going to use them when you get in section 2.7. With these first two, you could just pop them in the calculator, but the point is we're going to move on to where we have variables, and they're not going to be able to get into the calculator. And so we have to be able to get rid of the radical when we're solving equations. What happens is if the index, remember there's an implied index right here of 2. If you don't see an index, it's a 2. If the index and the exponent on the outside match, then they undo each other. They're inverses of each other. And what happens if you see that is that you end up with just the 4 that's underneath. Okay, and it makes sense. If you did the work up here, if you take the square root of 4, you get 2, and then 2 squared gets you back to the 4. All right, let's look at the next one. So same idea here. I have an implied index of 2. So now I have an index of 2, and I have an exponent of 2. These two are inverses of each other. They undo each other, and I'm just left with the 2 that's inside. Okay, again, those two you could just put in the calculator. This next one you cannot. Now I realize the calculator has letters on it, and you can hit the alpha key and get to those letters, but the main screen of that Casio, you cannot put the X's and Y's in. We can when we start graphing, but not in the main screen. So what we're going to do instead here is we know that our index is 2. Therefore, we have an index of 2, we have an exponent of 2. Those are going to undo each other, and we're left with x plus 1. Okay, so those are inverses. It's very important that we get used to that because we're going to use these quite a bit through the semester. Okay, same thing works with 3. It works with any number. If I have the cube root, let's say x, and I raise it to the power of 3, again, my index and my exponent match. They're the same. And so they actually undo each other, and I'm left with the x underneath. Also, it works the other way around, which we'll have to do as well, and the squares work the other way around as well. If I have the cube root of z raised to the 3rd power, still I have an index and an exponent that match, and so I end up with just z. Doesn't matter. I can come down here and do, I can do the 5th root of y raised to the power of 5, as long as those two match, as long as the index and the exponent match, then I just have the y that's underneath. Okay, so this is a radical equation. It asks me to solve. It has the square root of 3x on one side equal to 6 on the other. I can't put it in the calculator. Sorry, we have to do this by hand. We want x to be all by itself. That means that we have to get rid of the radical, right? Now remember, we have an implied 2 sitting here because we don't, that doesn't look like a 2, sorry. We have an implied 2 sitting there. If you do not see an index, it's a 2. And so I can get rid of the radical by squaring this side of the equal sign. However, remember with equal signs, with equations, whatever we do on one side, we have to also do on the other side. So I also have to square on this side. All right, so let's go ahead and take a look here. We had an index of 2 and an exponent of 2. So we are able to get rid of the radical by using inverses, and we end up with 3x on this side. On this side, 6 squared is 36. And now we need to just divide both sides by 3. And we get x is equal to 12. Okay, now the only thing with square roots is we do have to check our work, because sometimes we're kind of messing with algebra here by squaring both sides, or we're going to get to where we cube both sides. And so every once in a while, even though we get an answer, it doesn't really fit. And so let's go ahead and check. So we're going to come over here. Let's check our work. So we're going to have the square root of 3, and we're going to go ahead and put 12 in here. I'm going to put a question mark over the equal sign because I'm checking. And then on the other side, we have 6. Right, we're going back to the original problem. You want to always go back to the original problem. Okay, so that would give me the square root of 36 is equal to, I don't know, 6. And then the square root of 36 is 6. So I have 6 equals 6. And so that's good. It's good to go. So we're going to go ahead and take that answer of 12. All right, let me head to part 2.